Hello everyone and welcome to Geometry Lesson 4-7, Triangle Inequalities. The theorems in this lesson are similar to the converse of the Pythagorean theorem in that it gives us a relationship between sides and angles of a triangle. This lesson's first theorem says that if one side of a triangle is longer than another side, then the angle opposite the longer side is larger than the angle opposite the shorter side. And the second theorem says, if one angle of a triangle is larger than another angle, then the side opposite the larger angle is longer than the side opposite the smaller angle. Those were a little crazy, so let's paraphrase them both by saying that the longest side of a triangle has to be opposite the largest angle. Let's look at these two triangles for an example. In triangle ABC, side AB is the longest. Angle C is opposite that side, so it has to be the largest angle. Side AC is the shortest, so the angle opposite that, which would be angle B, is the smallest angle. That leaves angle A somewhere in the middle. It works the same way when we're given angles. In triangle DEF, angle F must be 90 degrees, making it the largest angle. Then the side opposite that angle, side DE, is the longest side. Angle D is the next largest, so the side opposite that, side EF, is the next longest. Finally, angle E is the smallest angle, so side DF, opposite that one, is the shortest. Not bad so far, right? Let's look at a couple problems that illustrate this theorem. In the first problem, we're asked to find the longest side. To do that, we need to find the largest angle. Angle R measures 62 degrees, making it the largest. The side opposite angle R is ST, so that has to be the longest side. In our next example, we're asked to list all of the sides in order from least to greatest. To do that, we need to first order the angles. Angle T is smallest, then angle S, and finally angle R. The side opposite angle T is segment RS, opposite angle S is segment RT, and opposite angle R is segment ST. So that's the order of our sides from least to greatest. RS, then RT, then ST. Now let's order some angles. Here in our first problem we have sides of lengths 13, 14, and 19, which is in order from least to greatest. Now we just need to decide which angle is opposite each of those sides. The smallest side, RS, is opposite angle T. Next smallest is ST, opposite angle R. The longest side, at 19, is side RT, which is opposite angle S. In order from least to greatest, our angles are T, R, and S. Let's do one more of these and I think we'll be ready to move on. In this triangle, side RT is shortest at only 11 units. Next is side RS at 19 units, leaving ST our longest side at 20 units. Angle S is opposite RT, angle T is opposite RS, and angle R is opposite ST, so that would be our order from least to greatest. Now for the triangle inequality theorem. The triangle inequality theorem says that the sum of the lengths of any two sides of a triangle is greater than the length of the third side. This theorem is really important because it tells us whether or not a triangle can exist with the side lengths we're given. If the sum of the other two sides isn't large enough, the two sides won't be able to come together with the third. It would look something like this. Generally, when I ask you to use this theorem, the problems will look something like this. I'll ask you not only to decide whether a triangle can exist with those side lengths, but I'll also ask you to combine this information with a theorem from lesson 4-5 to classify the triangle as obtuse, acute, or right. Let's try a few of these and see how you do. In our first problem, we're given sides of lengths 2, 3, and 4. To use the triangle inequality theorem, we take the two shortest sides, 2 and 3, and make sure that their sum is greater than the length of the third side. 2 plus 3 is greater than 4, so these lengths can make a triangle. Now we have to decide what kind of triangle this would be. Remember, square the longest side and see how it compares to the sum of the other sides squared. So we need to know how 4 squared compares to 2 squared plus 3 squared. 4 squared is 16, 2 squared is 4, and 3 squared is 9. 4 plus 9 is 13, and that's less than 16, so this triangle would be obtuse. Don't be afraid to review lesson 4-5 if you forgot how to classify these triangles. Our next example is a triangle with sides 2, 3, and 5. First we need to use the triangle inequality theorem to see if a triangle with these lengths can exist. The largest side is 5, so we need to know if 2 plus 3, the sum of the other two sides, is greater than 5. 5 equals 5, so this group of side lengths could not form a triangle. Make sure you remember that the sum must be greater than the third side, not equal to. Let's try one more of these. Now we have sides of length 2, 2, and 5. 5 is the longest, so we need to know if 2 plus 2 is greater than 5. It's not, so again, no triangle. There's one last type of problem involving this theorem that we need to look at. In these problems, we're given two sides of a triangle and asked to find the range of values that would work for the third. To solve these problems, we'll need to solve some inequalities. Think you're ready? Me too. In this problem, we have a 14-inch side and a 3-inch side. We know the sum of these two must be greater than the third side, so we get the inequality 14 plus 3 is greater than x, or 17 is greater than x. That inequality works for showing x as the longest side. But what if 14 is the longest side and x is one of the shorter ones? Then we know that 3 plus the other short side, x, has to be bigger than 14. So 3 plus x is greater than 14 would be our second inequality. Subtracting 3 from both sides leaves us with x is greater than 11. So x must be greater than 11 but less than 17. Let's do another one. This time our sides are 6 meters and 4 meters. If the missing side is the longest, then 6 plus 4 must be greater than x. So x is greater than 10. If 6 is the longest side, then 4 plus x must be greater than 6. Subtracting 4 from both sides leaves us with x is greater than 2. So in this triangle, x must be greater than 2 meters, but less than 10. One more example, because these are a little tricky. Here our side lengths are 18 and 12. If the missing side is the longest side, then adding these two sides together has to give us a number larger than that side length. So 18 plus 12 has to be greater than x, or 30 has to be greater than x. The missing side could also be shorter than one of these sides, which would make 18 the longest. Then our two shorter sides, x and 12, have to add up to be greater than 18. That gives us the second inequality, x plus 12 is greater than 18. Subtracting 12 from each side leaves us with x is greater than 6. So x must be greater than 6, but less than 30. That's all for this lesson. Remember, you can rewatch any part of this video that you didn't understand or that you'd like to see again. Thanks for joining me, and happy hypothesizing.